We saw that the squaring function f of x equals x squared is symmetric across the y-axis. This means that if we were to reflect the picture across the y-axis, we would get the same graph back. If we were to graph f of x equals x to the fourth power, we would see that it has the same symmetry. And the graph of f of x equals x to the 0, which is 1, is also symmetric across the y-axis. Notice how all of these functions are even powers of x. In fact, any function with an even exponent of the form f of x equals x to the 2n, where n is an integer, is symmetric across the y-axis. Because of this, we define a function whose graph is symmetric across the y-axis as an even function. We also saw that the cubing function f of x equals x cubed is rotationally symmetric around the origin. What this means is that if we were to spin the graph 180 degrees around the origin, we would get the same picture back. And if we were to graph f of x equals x to the fifth, we would see that it is also rotationally symmetric. In fact, the graph of f of x equals x to the first power, which is just x, is rotationally symmetric too. Notice how all of these are odd powers of x. And in fact, just like with even, any function with an odd exponent of the form f of x equals x to the 2n plus 1, where n is an integer, so that exponent is odd, is rotationally symmetric around the origin. So we define a function whose graph is rotationally symmetric around the origin as being called an odd function.